Good day everyone. Today's lecture focuses on advanced ground modeling, an important aspect of engineering geology, geotechnics, and site investigation. This is our module 2. Ground modeling actually is the process of developing a representation of subsurface condition. Now, how do we do that? You do that by using all available geological, geotechnical, hydrogeological, and geophysical data. In engineering practice, modern engineering practice, simply drilling a few boreholes is no longer sufficient. Engineers, geologists are expected to understand the behavior, the variability, and also that uncertainty associated with subsurface materials. Now, the importance of ground modeling lies in the fact that the ground is naturally variable and complex. You know that. We don't have an homogeneous earth. Now, unlike manufactured construction materials such as steel or concrete, soil and rocks are actually products we already know from geological processes that have occurred over millions of years. Therefore, their properties change from one location to another. So in this lecture, I'm going to be discussing engineering geological models, geotechnical models, spatial variability and heterogeneity, probabilistic ground models, data gaps and assumptions, management of uncertainty in engineering projects. Now, this topic is very important, especially in foundation engineering, slope stability studies, tunnel construction, dam engineering, environmental site investigation, offshore engineering. So, by understanding advanced ground modeling, you will be able to make better engineering judgments and reduce risk associated with subsurface uncertainties. At the end of this course, or at the end of this module, I expect that you should be able to differentiate engineering geological models from geotechnical models. You should also be able to explain spatial variability and heterogeneity in ground conditions. Describe probabilistic ground modeling approaches. Identify and manage data gap and assumptions. Apply advanced modeling concepts in engineering decision making. So let's dive in. Yeah, this is our introduction to ground modeling. Now, ground modeling refers to the development, I already said that, of a conceptual and analytical representation of subsurface. Now, the purpose of a ground model is to provide a clear understanding of one, soil distribution, rock distribution, groundwater conditions, geological structures, engineering properties, and potential hazards. So ground models are created using different sources of information, which includes the borehole logs, trial pits, cone penetration tests, laboratory testings, geophysical surveys, geological mappings, remote sensing, and historical site records. Now, a ground model is not just a drawing or diagram. It is an interpretation of the subsurface conditions based on available evidence. Ground modeling supports several engineering activities such as site investigations, foundation design, slope stability analysis, risk assessment, and construction planning. Engineering geological models focus primarily on the geological nature and history of the ground. Now, these models attempt to explain how the ground materials were formed or the earth materials were formed, the processes that affected them, their spatial relationship, their likely engineering behavior. Now, engineering geological models emphasize the interpretation of key components, which include lithology and stratigraphy. Lithology usually refers to rock or soil type, while stratigraphy refers to the layering and sequence of geological materials. I'm sure you already know that. For example, clay overlying sandstone, lateritic soil over weathered basement rock, marine clay deposits beneath reclaimed land. So that's it. So another thing again, it also helps with geological structures. Yeah, geological structures. Now, what are these geological structures? They include faults, fractures, folds, joints. Such structures may weaken the ground and affect stability. Like you already know, For we engineering geology, structures, let me not say structures are enemy kind of, when we see structures, it rings an alarm bell in our head because it can affect stability. Um, the next is the weathering profile. Weathering changes the strength and position of rocks. In tropical environments like Nigeria, intense weathering produces laterite, saprolite, and residual soil. These materials have engineering significance. Number four is hydrogeological conditions. Groundwater strongly affects slope stability. Yeah, it affects slope stability, soil strength, excavation conditions, seepage. And we have the geological processes. Processes such as erosion, sedimentation, and tectonic activity influence subsurface conditions. So engineering geological models are generally conceptual and descriptive. They form the foundation upon which geotechnical analysis is built. Here we talk about geotechnical models. Geotechnical models focus on the engineering behavior of soils and rocks. Unlike engineering geological models, geotechnical models are more quantitative and parameter based. The key objective is to obtain numerical values that can be used in engineering calculations and computer simulations. Important geotechnical parameters include one, shear strength. This determines the resistance of soil or rock to failure. Now, it is critical in foundation design, slope stability, retaining walls analysis. The second one is compressibility. That's the second parameter, compressibility. And compressibility determines how much settlement occurs under loading. Highly compressible soil such as clay can lead to excessive settlement. And the third one is permeability. Permeability measures how easily water flows through soil or rock. Now, this affects the seepage, it affects drainage, it affects consolidation and groundwater flow. The next is density, right? Density influences load bearing capacity and compaction characteristics. And the next one is that the fifth parameter is stiffness. Stiffness determines how much deformation occurs under stress. Geotechnical models are used in one, finite element calculations, finite element analysis, bearing capacity calculations, settlement predictions, and numerical simulation. So you can see how that these models are often represented mathematically and are essential for designs. Engineering geological versus geotechnical models. Let's look at them side by side. Now, engineering geological models and geotechnical models are related. However, they are different. I know most of the time people try to what's the difference between these? As we have already mentioned, engineering geological models. These models are process oriented. Yeah, they are descriptive, they are interpretative based on geological understanding. Now, their primary focus is understanding the origin and arrangement of ground materials. For example, a geological model may identify an ancient river channel, a fault zone, without basement profile, or marine sediment deposits. While the geotechnical models are usually parameter oriented, quantitative, analytical, engineering focused. They assign engineering properties to materials. For example, cohesion values, friction angles, elastic modulus, permeability coefficient. So what's the relationship between both models? Engineering geological models provide the framework. Geotechnical models provide the numerical values for engineering calculations. In practice, both models must work together. If the geological interpretation is wrong, the geotechnical calculations may also become unreliable. So, successful ground modeling requires collaborations between engineering geologists, geotechnical engineers, hydrogeologists, and geophysicists. That means you need a combination of all of these. Here, you need to understand the hydrological conditions, geotechnical conditions, and the geophysical conditions. Spatial variability in ground conditions. Spatial variability refers to the natural variation of soil and rock properties across space. This variation could occur both horizontally and vertically. No two points underground are exactly identical. The cause of spatial variability include the following. Now, I always like saying that um, the earth is variable, it's heterogeneous. And so that's the reason we look at all of these things when we are doing when and as engineering geologists. So let me look at the causes of spatial variability. Why? For example, okay, number one is depositional environment. Different depositional environments will produce different soil characteristics, right? Examples, we have river deposits, we have marine deposits, we have aeolian deposits, deltaic sediments. And you realize that all of these sediments, all of these deposits have different characteristics because of their depositional environment. So those are factors that are responsible for spatial variability. Two is weathering. Weathering intensity varies from place to place. Of course, this affects strength, density, and mineral composition. So you see, we don't have the same intensity of weathering everywhere. Number three is our groundwater conditions. I'm talking about the things um, that can cause that things that are responsible for variability. Now, groundwater condition changes in groundwater level affect effective stress. It affects soil consistency and then saturation. And then we have the human activities. Activities such as excavation, filling, and waste disposal alter ground conditions. So what's the engineering implications of all of this? Spatial variability can lead to differential settlements. We have a lot of that. There are a lot of examples of that in real life. Uneven bearing capacity, localized failure, increased uncertainty. For example, one section of a building foundation may rest on dense sand while another rests on soft clay. This difference can cause differential settlements and structural damage. Therefore, understanding spatial variability is essential for safe and economical design. So you're seeing where all this is coming in, right? Heterogeneity refers, okay, this is the heterogeneity of subsurface material. Now, this refers to non-uniformity in soil or rock composition. Subsurface materials are rarely homogeneous. I like to repeat that again and again. Examples of heterogeneity include alternating sand and clay layers, fractured rock masses, variable weathering zones, mixed fill materials. And we have different type of heterogeneity. Remember I told you that it could happen vertically. This variability could be vertical, it could be horizontal. Vertical heterogeneity, changes with depth. For example, you can have topsoil, the normal soil, you have clay, you have sand, weathered rock, fresh rock. And we can have horizontal heterogeneity, which is changes across lateral distance. One side of a site may contain soft clay, while another side may contain dense sand. We have challenges, yes. There are challenges created by heterogeneity. And what are these challenges? Difficulty in predicting subsurface conditions. Increased uncertainty between boreholes. So you can have a borehole and another one there, and you're not even having the same log. More complex engineering analysis, right? And higher risk of unexpected conditions during construction. So in engineering geology, engineering, heterogeneity affects foundation performance, slope behavior, tunnel stability, and seepage patterns. Therefore, engineers must collect sufficient data to characterize heterogeneity, adequately. Probabilistic ground models. Traditional ground models often assume deterministic values. For example, you can have correction at 25 kilopascal and angle of friction angle at 30 degrees. However, in reality, soil properties vary. So probabilistic ground models recognize and quantify uncertainty. It quantifies uncertainty. Instead of assigning a single value, they assign a range of possible values. Now, why probabilistic models are important? Because the subsurface is uncertain. Probabilistic models help engineers understand risk, estimate variability, improve reliability, and make informed decisions. There are common probabilistic methods. I'll talk about them. We have the Monte Carlo simulation. This involves repeated random sampling to estimate possible outcomes. The Bayesian methods, this updates predictions as new informations become available. And then we have our geostatistics, where geostatistics analyzes partial relationships among soil properties, and then random field modeling. This represents partial variation mathematically. And the advantage is this: we have better risk management, more realistic predictions, improved reliability based design, better understanding of uncertainty. So probabilistic approaches are increasingly important in modern geotechnical engineering. So let's go deep into our probability, the concept of probability distribution. Now, in probabilistic modeling, soil and rock properties are represented statistically. This requires understanding probability distributions. A probability distribution describes how values are spread around an average. We have our common distributions. One, normal distribution, also called the Gaussian distribution. It forms a bell-shaped curve. Many geotechnical parameters approximately follow normal distributions. Then we have the log normal. We have the log normal distributions, where now this is used where values cannot be negative. This is usually common in permeable and hydraulic conductivity analysis. Number three, we have the the Weibull distribution. Number three, we have the Weibull distribution. The Weibull distribution is often used in reliability and failure analysis. When you're doing your analysis, maybe failure analysis, you usually use the Weibull distribution. So what's the importance? Okay. Now there are important statistical parameters to note. That's we have our mean. Mean means average value. I know you know that. Standard deviations. The standard deviation measures spread around the mean. We have the variance. The variance square of standard is the square of standard deviation, and we have the coefficient of variation. Now that's the ratio of standard deviation to mean. This indicates relative variability. I think these are things, I know you might have done this in your early statistics. So, but I'm just recapping it. Why? Because these are things you're going to be applying as engineering geologists. And we know that it's actually an applied science anyway. Importance in engineering. Now, what's the importance of probabilistic distribution? Now, it helps engineers to quantify. Yes, it helps us to quantify uncertainty. Statistics, probabilistic distribution help us to quantify uncertainty. It helps us to predict possible ranges, estimate failure probability, improve design reliability. Now, understanding statistical variability is essential in advanced ground model. Very, very essential. Very, very essential. Statistics is very, very essential. Data gaps and assumptions. One of the greatest challenges in ground modeling is incomplete information. Why? Because, investigating the subsurface is expensive. So most of the times, engineers really have complete data. This creates data gaps. Now, the causes of data gaps include one, limited boreholes. If only if we have a few, if what okay, only a few locations may be investigated. So you might say that we cannot how much borehole can one drill? How much borehole is even available on that site when you go there? We also have budget constraints. Extensive investigation may be too costly. It may be too costly. Number three is difficult site access, like areas like swamp, offshore areas, urban locations may restrict investigation. We're not able to go do detailed investigation because of accessibility. Then number 4 is incomplete laboratory testing. Some parameters may not be tested, so those are part of not that's part of the data gap. But then we have common engineering assumptions because of this insufficient data. Assumptions are often necessary. Example includes continuity between boreholes. You know, so if we have a different borehole here, borehole there, we'll be able to kind of make assumptions about the continuity of these boreholes. Assume uniform groundwater conditions, and also sometimes we assume constant soil properties and similarity of adjacent layers. Now there is a risk. I thought it's an assumption, but of course we have risks to assuming. There are risks to assumptions. Incorrect assumption may lead to foundation failure. Excessive settlement, slope instability, construction delays, cost overrun. So assumptions must always be documented and justified. So you're not just going to be doing random, what's it called, random assumptions. The assumption should be based, and justified based on things we have on ground, and there are conditions that are on ground that helps justify your assumptions. Managing uncertainty and data gaps. Yeah. Since uncertainty cannot be completely eliminated, we need to focus on managing it, right? Engineers need to focus on managing it. Several strategies are used, and I'll be talking about them. One is additional site investigation. More boreholes and tests improve confidence. You know that, right? So if you're able to have more data, or let's say you get information from more number of boreholes, it will be easier to be able to make closely accurate assumptions. Number 2 is what? Use of geophysical survey. Yes, as we cannot always assess the underground, we will not always want to drill, we can use geophysical surveys. Now these geophysical methods include the seismic refraction, electrical resistivity, ground penetrating radar. This can provide continuous subsurface information. You see that now. Now even though we're calling it an assumption, you see we say it has to be justified. So you're going to use your geophysical methods. When is your geophysical method? Now we're not even still seeing the subsurface, but with our geophysical methods we can interpret. We can interpret and augment our borehole data. Number 3 is sensitivity analysis. This examines how changes in parameters affect design outcomes. How changes in parameters affect design outcomes. So those are different things, you would different, when we're assuming, we'll tweak some parameters and then see if these tweaks, what if it's not exactly as we're saying, if it's at this range, what's going to be the outcome. Then we have our conservative design. Engineers may adopt safer assumptions where uncertainty is high. So most of the time, sometimes you want to be as conservative as possible, because especially when you consider that the risk of being wrong can cost you a lot. Observational method, we know that the design is adjusted during construction based on observed condition. This method, I already told you in last module, that is common in tunneling, deep excavations, and slope stabilization. Yeah, talk about observational methods. Continuous modeling of this. Now the truth is this: ground models should evolve as new information becomes available. This approach reduces risk and improves project performance. So, applications of advanced ground modeling. Advanced ground modeling has wide applications in engineering practice. One, I said tunneling engineering. Now, how does that help? Ground models help predict rock quality, fault zones, water inflow, and excavation stability. So, when you do a ground model, you can have an idea of all of these things, which helps you to make a better decision. And another thing again is the offshore foundations used in oil platforms, wind turbines, coastal structures. So marine sediments are often highly variable, very variable. So we need to do ground modeling for such. So you can see the reasons why we cannot just ignore ground modeling. Landfill designs. Now ground models assess permeability, contaminant migration, stability, and so all of these things is necessary. Like if you want to site a landfill, I remember in one of our discussions in the group, we talked about the fact that when you want to site when you want to site a landfill, you're looking for a place with very low permeability. I think that was an offshoot of one of someone's presentation. You're looking for a place that have very low permeability. So landfill design, when you want to ground, ground model access. Ground model access, will assess permeability, will assess contaminants migrations, and also stability of that area to be used as to design the landfill. Then another place we can apply ground modeling is for slope stability studies. We use it to evaluate landslide risk. How about dam engineering? These are all things I've mentioned. Dam engineering. Um, in dam engineering, ground models assess foundation conditions, seepage potentials, stability, and we have the urban infrastructures, which is important in roads, bridges, railways, high-rise building. Accurate ground models reduce construction risks and improve safety. We have a case study. Yeah. So now this is a case study of a coastal foundation project that was constructed on soft marine clay. And this is what the problem was. We have highly compressible marine clay, variable thickness of soft deposits, and high groundwater level. Now, the traditional deterministic analysis produced inconsistent settlement predictions. As a result, we had to think of another investigation approach. So what was used? A combined approach was used. A combined approach was used where borehole data, comb penetration test data, laboratory testing, geological interpretations, and probabilistic model. All of these were combined. And when all these methods were combined, the analysis showed significant variability in undrained shear strength, compressibility, thickness of soft clay, and therefore, so the outcome now, using probabilistic modeling, one, settlement prediction improved. Then the foundation design became more reliable because now we had something more quantitative. Risk was reduced and construction planning improved. Now, one of the lessons one could learn from this particular project was that there's an importance of having adequate investigation. You can't just use one method. This combined method really helps here, and it helps in also understanding variability. You have to always be in the back of your mind when you're handling a project. You need to understand the variability, the heterogeneity, the inconsistencies, the uncertainties that can pop up, and then integrating geological and geotechnical data. Those are lessons you need to learn, that we need to do a combined approach, and then managing uncertainty scientifically. Have quantitative. I told you we have quantitative results, quantitative parameters that can help us make more certain, or what I say, that can help us manage uncertainty better. So let's do a recap. In summary, ground modeling is essential in engineering geology, geotechnical engineering. And now, so far, we learned about engineering geological modeling, that this focus on geological history, processes, and interpretation. Two, the geotechnical models that focus on engineering parameters and numerical analysis. Three, spatial variation and heterogeneity. Subsurface materials vary naturally, increasing uncertainty, and then the probabilistic models. These models quantify uncertainty and improve reliability. Data gaps and assumptions. Incomplete data require assumptions, but assumptions also introduce risk. And as a result, how do we manage this uncertainty? Additional investigations such as geophysics, sensitivity analysis, observational methods help reduce uncertainty. So the key message here is this: The ground is inherently uncertain. The earth is variable, is heterogeneous. So a lot of uncertainty. And successful engineering depends on understanding and managing that uncertainty. And that's sometimes that's the problem with when we have people that are will I say quack, people that don't know what they are doing. They tend to most of the time um just make some assumptions, not scientifically, not knowing details. And that's why you see many houses now, they build houses and before you know if you hear houses collapsing, you see foundational issues. Why? Especially in places that have very peculiar geologies. Because of this heterogeneity that they don't put into consideration, we have a lot of problems. But when an engineering geologist, when someone like you is consulted, as a consultant, you'll be able to consider every necessary thing that should be considered so that we can have less uncertainty and better outcomes. Yeah, you have an assignment. That's to compare engineering geological models and geotechnical models with examples. 2, explain how spatial variability affects foundation design. 3, discuss the role of probabilistic modeling in reducing geotechnical uncertainties. And 4, suggest strategies for handling data gaps in site investigations. Yes, you can see it there, it's on the screen. Yes, so we'll discuss it. We're not discussing it. You're going to make it as an assignment. Do your assignments, yeah. You will submit it, and then we can discuss it when we're going to meet for discussions. So all the assignments I'm giving, you need to do them properly, and then we will now also discuss them as well. Thank you. Now the thing is this, I mean, in answering these assignments, yeah, I encourage you to use practical examples and diagram where possible. Yes, possible where possible to use diagrams and practical examples. Thank you. See you in the next class.